So today we're going to do logic gates. Hopefully this will be an easier lesson than some of the last few. I think a lot of you guys who are here for Circuit Lab especially will find this a lot more directly applicable to the things that you want to be learning. But the principles that we've talked about for everything else are still important, and you should remember that because you're here to learn how to use circuits in the real world, not just ScioLi. I emphasize that a lot. So classroom code, just keep it there in case anyone wants it. So we are having an extra lesson today. I will be there this time. I'm not gonna mess it up again. It'll be on op amps, which are in some. Okay. It's on op amps, operational amplifiers. That's a major topic for Division C. Actually, a lot of people mess it up. Okay, can someone? What is going on
I
there?
got it. I'll figure it out.
Um, yeah. So op amps come up a lot in ScioLi Division C. And from what I've seen, this is the thing that people mess up the most in Division C Siley, actually. They really don't know what they're doing. It will be recorded and it will be posted. I'll make sure of that. So this is op amps are probably the most difficult part of Division C Siley, but they really should be the easiest part because op amps are very simple circuit components to think about. So only one more class after this, and actually we're pretty flexible about what we can cover in that last class. So if there's any topics in particular that anyone really wants us to talk about in a lesson, just let us know because we can plan the lesson around that and we want to teach what you guys want to know. So
Yeah.
just let us know.
I'll send out a form sometime after this lesson and we'll cover like what you guys
Yeah.
want to do.
Or you can just say it in the chat as well.
Or yeah, you can message me in chat at the same time. That's fine.
So let's review what we talked about last time. So the MOSFET, the metal oxide semiconductor field effect transistor, is a very important circuit component. Okay. So can someone remind me why we put the oxide between the metal and the semiconductor? Why do we put that layer of oxide there? Acts as an insulator, exactly. So if you remember the architecture, oops, remember the architecture of the transistor, you had layer of that layer of metal, a layer of oxide, and then the big block of semiconductor. And we don't want any current flowing from that layer of metal into the semiconductor, okay? So how do we control the size of the channel that flows from drain to source? If you remember what the oops, this was a mess. If you remember what the voltage does, this is true, but voltage, what voltage in particular? If you remember what the transistor looks like, we have that big block of semiconductor. Oh my goodness, that is slanted. We have that big block of semiconductor, like okay, like I'm not gonna draw it. I tried my best. The gate voltage, yes, the gate voltage. So for us, there's two types of MOSFETs of interest. Okay, there's a PMOS and an NMOS. What's the key difference in their structure? Like in their and they how they yeah, agam D2 agam. I don't know.
In PMOS, there's N type on the two corners, and then the rest is P type. And in PMOS, it's P type on the top left and right, and then the rest is NMOS. I mean N type.
Yes. Yep, exactly. So that's true as well, Cyril. That's like how they work. That's true. But yeah, the channel shrinks and grows in opposite ways, and the actual like physically what's different is the charge carriers are different. So in an NMOS, your tiny doped regions, I am gonna draw it actually. You have your transistor block right there. You have so this the majority is P, then up here is N, and up here is N, and current flows from an N shape to an N from an N thing to an N thing. And so it's flowing as electrons. Okay, this is NMOS. Okay, but a PMOS has at the top right here, you have a P type and you have a P type, and the majority of it is N. And so what's flowing is the positive charges, the holes. It's like bubbles. Okay. So BJTs do not work. They're not field effect transistors. So a MOSFET, the FET stands for field effect transistor, a BJT bipolar junction transistor. In practice, actually, you use it similarly, like a switch. So we can turn it on to really high resistance, off really low resistance. Or sorry, other way around. But in practice, you can use either transistor a lot of the time. MOSFETs are just way more important because MOSFETs you can make way tinier. Remember that plot I showed in the last lecture? MOSFETs are what we see in most actual real world circuit. So BJTs are also useful and important. We're just not going to talk about them here. So which one of them has their gate closed when we apply a high gate voltage, a PMOS or an NMOS? Which one is closed at high gate voltage? Steph Curry is the GOAT. Oh, it's like 50-50 guesses. It's PMOS. Okay. So remember, for an NMOS, I guess we'll get into it in a second. But when we have a high voltage, oh sorry, I lied. It's PMOS. PMOS. When a high voltage is applied to a PMOS transistor, the gate is closed. When a high voltage is applied to an NMOS transistor, the gate is open. Okay, and this will make more sense in a second. And we're gonna think about them as on or off. Okay. So if a transistor is on, what kind of resistor is it like? Is it like a really big resistor or a really tiny resistor? If a transistor is on, is it like a big resistor or a small resistor? Think about what on means. So if for a resistor has V equals IR, okay? On means when I apply a lot of voltage, I also get a lot of current. To get that, I need a small resistor, okay? A big resistor would mean for a lot of voltage, I only need a tiny bit of current. So a big resistor is like an off transistor, a small resistor is like an on transistor. Okay, and I'll show this again in a second. And now, similar question to earlier, what controls whether the transistor is on or off? What directly controls that? Kind of already said it. Not a rectifier. A rectifier is something else. Voltage, that's true. Voltage where? Gate voltage, yeah. I'm just looking for the buzzword here. Okay. And so again, is a PMOS transistor turned on with a low or a high gate voltage? What turns on a PMOS transistor? Low. And does on mean the resistance is low or the resistance is large? Low. Exactly. You got it. Well, I guess people were still answering the question. So now let's recall the CMOS inverter. This is what we ended the last lecture on, okay? The CMOS inverter. C is for complementary. We have two MOSes, two metal oxide semiconductor devices that are opposite each other. One is a PMOS, one is an NMOS. Okay? So what would happen? Okay, so to be clear, in this device, if Vin is high, so say Vin is 5 volts, we basically get a thing that has a very large or small resistance. If Vn is high, the gate voltage here is high. Is the PMOS on or off? If Vn is high, is the PMOS transistor on or off? Off, okay? So that means this resistor, this transistor is like 5 million ohms, we'll say, okay? And in practice, it is around that. It's about 5 million to 50 million ohms. It's about the resistance that it displays. So that means the NMOS is on, so the NMOS will be about 25 ohms, okay? You put 5 volts up here and 0 volts down here. And remember, the gate is completely isolated from the transistor. Because it's a field effect, it just like kind of gives instructions. It's like makes a phone call to the source and drain and says, hey, make sure you have big resistance right now. Make sure you have small resistance right now. But other than that, the gate has no actual direct current involvement. In fact, when we do transistor circuit analysis, we always assume no current flows into the gate, okay? So in this 5 volts, big resistor, small resistor, 0 volts, what's the voltage right here? What's the voltage in between the resistors? Or in this case, in between the transistors? About 0 volts. It's like 0.001 volts. It's just a number very close to 0, okay? Now, if this is instead 0 volts over here, this is instead going to be 25 ohms. This is instead going to be 55 million ohms, okay? And then V out is going to be actually 5 volts, okay? So this device just inverts the voltage. But that's because we put the PMOS on top and the NMOS on the bottom. What if we put the NMOS on top and the PMOS on the bottom? Okay, well, I'll just walk us through it again, but we should get the logic by now. Oops. So oops, sorry. You're just bugging out a little. Okay. So if Vn is high, the NMOS is a small resistor and the PMOS is a big resistor, okay? So if you think about if I swap these two, if I instead make this guy NMOS and I make this guy PMOS, okay? Then the transistor on the top, when I have a high Vin, will be small resistor, okay? So if Vn is high, if Vn is 5 volts, then what I have is a big resistor, say that's 5 million, and then we have another resistor that's like 25. And then what's the voltage here in this case? Oh, sorry. Sorry, that should be, I messed that up. Uh, so this should be 25, and this should be 5 mil. Okay? If we swapped the NMOS and the PMOS. So to be clear, we're not assuming this. This is the behavior of the transistor. Okay, we're modeling the transistor as a resistor that's really big or really small. Okay? And that's because just based on the behavior that we showed in the last class, if the gate voltage is really low, it's like the channel doesn't even exist. And so no current can flow in an NMOS. If the gate voltage is really high, we've opened that gate, we've formed channel for current to flow in, and so current can flow. If you're confused about that, I suggest you review the last lecture's content. That was the focus there. But yeah, so in this case, what's the voltage in between these two resistors? If we swap the NMOS and the PMOS, this is what we have. And what's the voltage between them? Someone tell me. There is. Ground is down here. So in this case, ground will be right here. So the answer is it's 5 volts. Okay, it's 5 volts. Okay, so we've made a nothing machine. We put in 5 volts and we get out 5 volts. But notice how the gate is again entirely isolated from this voltage right here. We've taken 5 volts and we've created a new 5 volts, but I can do whatever I want to the 5 volts over here. I can mess with it a lot, and I can mess with these 5 volts, but they're not going to interact with each other, okay? And the same thing holds true for the 0 volts case. This is why we call this a buffer. It takes whatever's going on before the transistor at the gate side and isolates it from whatever's going on after the transistor. So when you build circuits in practice, and I mentioned this because it's a really, really important thing that a lot of people don't take into account when they build a circuit. I don't know if the detector building is an event this year. Is it?
It is
Is
not.
it still here? It is not. Okay, well, the detector building's gone. Thank God for that. I hated that event. But if you're ever building a detector building circuit, or if you're ever building a circuit in Circuit Lab, a lot of the time you'll find that there's some weird oscillations happening in your output, or you're getting some really weird behavior as you attach more components. That's because you need a buffer. You need something where these two guys are swapped to basically isolate one part of your circuit from the next part of your circuit. Okay. But more generally, what I'm trying to say here is that a transistor allows us to make an input and an output that are independent of each other. Okay. And that's really what logic gates are all about. Okay. What I mean by isolate the voltage is, so suppose I made a circuit where I had a 5-volt battery and a 10 ohm resistor. Okay, 10 ohm resistor. So in this case, the current is half an amp, right? We should be able to see that pretty quickly. But what if I wanted to add another 10 ohm resistor? Say I have a second light bulb I want to power. Well, I want to add that resistor right there. But now I have another 10 ohm resistor. So now the current flowing through the circuit is less. Now there's 0.25 amps flowing through the circuit. Okay? And so that means I'm not giving as much power to these resistors. If instead I had something where I could send those, I could have this battery right there, then I have something that isolates it, some like break in the circuit. And then over here, I have another 10 ohm resistor. Then I can make it so that they both still get the same amount of current. Okay. Basically, I duplicate the voltage so that I can still give the same amount of current to both. And I don't change the amount of current I'm giving to one element by adding more elements in. Okay. Well, voltage is infinite. Remember, voltage is not power. Okay. Voltage is just the potential to do work. That's why we call it potential. Okay. Anyways, let's talk about the logic gates now. Let's get to the point of the lecture. I just wanted to mention that because that's a really important bit of actual circuit design that you guys need to know. So the NAND gate, we call this NAND. In other words, not AND. Okay. What a gate does is we take two or more inputs and we spit out some output. Okay. We always talk about gates, if you're not doing quantum computing, we always talk about gates as binary things. Okay. A 1 is high and a 0 is low. High means 5 volts, 0 means low volts. There's other conventions. For example, there's a back in the 1960s and earlier, when they were doing nuclear physics, they have a thing called the nuclear instrumentation module, where high in that case is 0 volts and low is -1 volt. That's kind of stupid though, and it's an outdated convention. This is called the TTL convention, truth to logic. 5 volts is 1, 0 volts is 0. Okay? So the simplest logic gate to build is not the AND gate or the OR gate that some of you guys might have heard of, but actually the NAND gate. And the NAND gate does this. If I have 0 and 0 as my inputs, I spit out 1. If I have 0 or 1, I spit out 1. If I have 1 or 0, I spit out 1. But if both my inputs are high, if I have two 5-volt inputs, I spit out 0. Okay? So let's try to build a NAND gate with our transistors. Okay? So we need two inputs and an output. Okay? Let's start by just connecting two NMOS transistors to A and B. And let's connect them like we would a series resistor. Okay? And now let's consider the four possible combinations of A and B. Okay? So combination 1 is right here. Focus on this one right now first. If A is 5 volts and B is 5 volts, we've turned the transistor on for both of these. And so both of the resistors that we replace them with are going to be small, right? An NMOS is turned on for high voltage, and an on transistor is a small resistor. Okay, so we have this right here. If A is 0 volts and B is 5 volts, the first transistor is off and it has a really big resistance. The second one is on and it has a small resistance. Okay, same thing here. If A is 5 volts, the first one's on and has a small, the second one's off and it has a large. And the last one, if they're both 0 volts, then they're both large. Does it make sense how we get to these resistance values from A and B being their given voltages? Are we all clear on that? Does anyone not understand that? If you don't understand, you got to say so. This is the BP part of the lecture, so I don't want to move on unless we're all clear. No one's saying anything. What are signal pins?
Could you
Chris,
re-explain?
yeah. I'm not sure what you're asking, Chris, but okay. So remember that depending on the value of this voltage at the gate, this transistor is either like a really big resistor or a really small resistor. Okay. In the case of an NMOS transistor, looking at the N, if this voltage is high, if this voltage is 5 volts, then this guy acts like a small resistor. Okay, like a 25 ohm resistor. Okay. But if that voltage is low, then it's like we're closing the gate and it acts like a really big resistor. It's resisting a lot. So it's like 5 million. Okay, redraw all that out. So what we're doing here is we're looking at the possible combinations of A voltage and B voltage. Okay. If the A voltage is high, 5 volts, and the B voltage is high, also 5 volts, then both of those resistors are this case right here, the small resistor case. And that's why we replaced transistor M1 with a small resistor and transistor M2 with a small resistor. If they're both 0 volts, they're both low, and so they're both acting like the 5 million ohm resistor. And so we replace them with two big resistors. And the other cases are doing the same thing depending on the value of A or B. The key takeaway here is that this case has an equivalent resistance of about 50 ohms. The rest of these are like 50 million, 100 million. So these three on the right, all three of these cases are big resistance, okay? Very resisting. This case right here has a small resistance, okay? 50 is a lot less than 50 million. 50 million is not that much less than 100 million, but 50 is a lot less than them both, okay? So the situation in which both A and B are high has a lot smaller a resistance than the other two situations. Okay? Yes, so 0 is where the resistance is low, and 5 is where the resistance is high for an NMOS. But for a PMOS, it's the opposite. Okay? So now we're doing the exact same thing, but now we have two PMOS transistors that are in parallel. It's not an AND gate, it's a NAND gate. It's very important that we make that distinction. So here now we have two PMOS resistors. Okay? If the PMOS resistors both have 5 volts, they're both off, and off means high resistance. If they both have 0 volts, they're both on, and on means low resistance. So the equivalent resistance here is about 12.5. Here, if you use the formula, okay, you don't have to calculate it yourself. If you use the formula, it's about 24.999, so it's about 25. Here, it's the same thing using the formula for parallel resistance, also about 25. But here, we're actually going to see it's about 25 million, okay? So the resistance on the left, in the case where they're both 5 volts, is way bigger than the resistance on the right. Okay, so now we have a pair configuration of PMOS and a configuration of NMOS that does something. Now let's combine them, okay? Let's combine these two together. And we'll go case by, we're gonna go really slow through this, just case by case. So first, if A is 0 volts and B is 0 volts, okay? The NMOS is on or off. Is the NMOS transistor on or off here? If A is 0 volts, sorry, in the case of an input being 0 volts, will the NMOS be on or off for 0 volts gate? Off, right. And will the PMOS be on or off with the gate voltage of 0 volts? On, exactly, okay? If an NMOS transistor is off, or if a transistor in general is off, it has a big resistance. So that's why those two are big. The PMOSs are on, so they'll have a small resistance, which is why these two are small, okay? So in this configuration, can we see why Vout is very large? This part right here has a very small resistance, okay? This part right here has a very big resistance, okay? Big. So do we see why Vout would be large here? Are we all clear on that? Okay, I'm gonna assume we're all clear on that. Let's move on to the next case. If A is 5 volts and B is 0 volts, we again use the same logic, okay? So this PMOS transistor is going to be off, okay? Because it has a high gate voltage. This PMOS transistor is going to be on because it has a low gate voltage. So since this is off, we replace it with a big resistor. Since this is on, we replace it with a small transistor. This NMOS, is this NMOS, M3, is this one going to be on or off? Tell me in chat. Is it going to be on or is it going to be off? On, right? This one's going to be on. And is this transistor going to be on or off? Off, right. And so since this one is on, it goes to 25. Since this one is off, it goes to 50 million. Okay? Now notice, this is the equation for parallel resistance. So this whole combination right here is equivalent to about a 25 ohm resistor. Okay? Then we take V out right here. And then down here, we have 25 plus 50 million, which is about 50 million. Okay? Re-explain the PMOS part. So remember, a PMOS transistor turns on when we apply a low gate voltage, and it turns off when we apply a high gate voltage. It's the opposite of an NMOS transistor. Okay? So since we have a high gate voltage on this guy's gonna be off. Since we have a low gate voltage here, this guy's gonna be on. And so now we know on or off, we can just replace it with the corresponding resistor. Okay? What is a Sure, I can turn on AI companion. Okay. Um, so it's talking to me. Okay. Um, okay. So now let's look at the next case. This is the exact same thing as the last case, but we've just like turned it around, right? And so again, the resistance of this whole part right here, this whole box, is about 50 million. Okay. Oh, sorry, I don't know why I said that. The resistance of this whole box right here is about 25. The resistance of this whole box right here is about 50 million. Oh my God, 50 million. Okay. And so V out is again it's gonna be much closer to 5 volts than it is to 0 volts. The interesting case is when they're both 0 volts. Okay. Now the resistance up here is about 12.5, and the resistance down here is about 100 million. Okay. And since we take V out between them, V out is gonna actually be a lot closer to wait a minute. Oh, yeah, there's something sus here. I think I made a mistake in the slides. But uh-oh. Okay, so let me back up for a second. So
Oh, there. No, yeah, that's fine.
this is okay. I'm just gonna there might be a mistake here. I apologize for that. But this is what I want to emphasize. Okay, if you're confused, if you're completely lost, this is where I want to kind of pull you back in and clarify what's going on. So this right here is a NAND gate. Okay, this is the actual structure of a NAND gate. Okay, and the NAND gate does this. If it's 0 and 0, we output 5 volts. If it's 5 and 0, we output 5 volts. If it's 0 and 5, we output 5 volts. But if both are high, if both of them are 5 volts, we output 0 volts. Okay? This is the exact same thing as it's called a truth table, as I showed right here. 0, 0 is 1. 0, 1 is 1. 1, 0 is 1. But if we have two ones, it's 0. Okay? So this is the simplest possible logic gate to draw. And actually, the NAND is what we call a universal logic gate. You can make any other logic function out of only a NAND gate. Okay? So in practice, we don't draw all this transistor mess. We draw it just as this one pretty thing right here. Okay? We draw A and B going into this structure. It's like a little half egg with a little bubble at the front. This is called an inversion bubble, and Jay's going to talk about it in a second. But let me go back to the slide like someone asked. This slide. Yeah. It looks like queso, but with longer legs. Okay.
Crazy.
So yeah, I definitely messed up the transistor explanation. I'm really sorry for that, because I know it's confusing and that probably made it worse. But um, this is like you should be able to go through and just reason through each individual case. High voltage, that means NMOS is on, PMOS is off. Off means big resistance, on means small resistance, and then just solve it like a regular resistor circuit. Okay. And it's important to keep this intuition in mind because transistors are things called they pull up outputs or pull down outputs. And when you're actually building circuits with logic gates, it's important to remember this is how they work. Particularly when a lot of people try to wire two wires together instead of using an OR gate, that doesn't work because they pull up and pull down outputs. That doesn't need to make sense to you, but just keep this in mind if you're ever building circuits. So I'll go ahead. Oh, and that last thing is we're not going to talk about the transistor structure of all the other logic gates, but ultimately, at their core, they are made of transistors. They're made of MOSFETs, a bunch of different MOSFETs doing a bunch of different things. For example, the exclusive OR XOR is like this. You can see, and some of these are actually inverted. So XOR needs about 12 transistors to implement. It's a lot more complicated than the NAND. So we're not going to talk about the transistor architecture, but remember, these logic gates are still made of transistors. Okay. I'm going to stop my screen share and give it to Jay.
Okay. All right, yeah, I'll screen share from here.
And if there's any questions about what I talked about, I can answer them in chat now. So
All right, let me slideshow here. All right, Ishaan gave a great explanation about how we use transistors to make our logic gates. But when you're actually using logic gates in, let's say, Science Olympiad, you won't need to know the transistor architecture. Instead, we'll be using these symbols here to kind of describe how these logic gates are. And you'll pretty much only be dealing with these from here on out. So good news, if you were confused about transistors, we're kind of past that now. So let's cover our first gate. This is our simplest gate in terms of inputs. So it only takes one. And this is what we call our NOT gate. Important thing to note here first is that, again, one input and this inversion bubble here. I think it's, yeah, there, okay. But what this NOT gate does, it just inverts. So if you have a high voltage, in this case, and from here on out, when I say high voltage, I'm going to say 1, it'll give a 0. And if it's a low voltage, which will say 0, it'll give a 1. So it flips it, right? And as we said earlier, with the CMOS inverter, this is exactly what it does. And this is a CMOS inverter. So, okay. What I want you guys to pay particular attention to is this bubble here. I think it's called the inversion bubble, but we use this to add NOT gates to other components to invert their outputs. And we'll see an example of that in a second. Okay. I don't know why that says NOT at the top. This is an OR gate. OR gates, I think some of you guys might have heard this one before, or an AND. So what an OR gate does is that it takes either A or B, and if one of them is a 1, then it'll output a 1. And you can see down here what the results are of all the different combinations that you can have. So you can see as long as there's a single 1 in A, B, or both, it'll output a 1 here. So if A or B is 1, the output will be 1, and that's where the OR name comes from. Yeah.
Sorry, Jay,
sorry.
Go back. I think you skipped the AND slide on accident.
I did?
Yeah.
What? Maybe.
It's before.
Oh, I did skip the AND slide. Okay. Yeah, I can just cover that one next. It's fine. Okay. Let's see. Yeah, here you go. All right, thanks. All right, so this is our AND gate. So Ishaan talked a lot about the NAND gate. And what the AND gate is just the, I guess, uninverted version. So when we see here, if both A and B are 1, then it'll output a 1. And this is the opposite of the NAND gate. I think it's somewhere here, where both of them, or if both of them were 1, it output 0. So let's see, that N before it kind of symbolizes that there's a NOT before this gate, and it's inverted. So let's see. So are you guys clear on those basic 3, and, or, and NOT? Oh, okay. Yes, okay. Yeah, so this stuff is going to be a lot more simple than transistors, and you can just pretty much memorize everything from here. Oh, will we learn binary? We will not be learning binary unless some people like request it for tomorrow or Friday. Yeah. Let's get into our inverted logic gates here. So these are the inverted, or I guess the NOT versions. As you can see here, when we add this inversion bubble, it will flip the output. So instead of 2 zeros on the OR gate giving a 0, it gives a 1, and everything else is a 0. You don't need to actually memorize either of these, the NAND and the NOR. Instead, you should know that when you have this inversion bubble here, it just flips the output. And you can see here, AND is the same thing, where it was supposed to output a 0, it outputs a 1. So I would strongly recommend, instead of memorizing all these different tables, you just need to understand the OR, the and then what this inversion bubble does. Okay. Yeah. All right. Here is our final gate that you guys will need to know. This is going to be our exclusive OR gate, or SOR. There's multiple pronunciations, I think. But what this gate does is that if A and B are different, yes. I don't know if I made that clear. This is supposed to be memorized, what they do. But you can kind of guess what they are, and I'll give you a brief recap before we go to our Kahoot later. So exclusive OR, all it does is if A and B are different, it'll output a 1. So you can see here, 0 and 0 will output a 0, 1 and 1 will output a 0. But if A and B is 1 and the other one is 0, then it'll output a 1. And exclusive OR, when it invert it, becomes XNOR, and it's just the inverted version of XOR. So again, don't memorize this one, memorize this. And you can use this inversion bubble to figure out what the actual XNOR gate does. Let's see.
And one thing I'll mention about XOR and XNOR, So back in the when logic gates were first becoming popular and digital design was first becoming big, actually you did all digital circuit design with XOR and XNOR gates. You didn't actually use NAND and or all the common ones. XOR was the simplest thing to do it with because although XOR has a complicated transistor architecture, it can actually accomplish the most things with a very few number of inputs because it does what we call a nonlinear operation. So if you ever find yourself doing digital design, if you ever find yourself trying to build circuits, XOR is a great place to start. In the modern day, where we have FPGAs and other configurable logic devices, we don't use this as much. But when you're building circuits on a breadboard, XOR is one of your most important logic gates that you have available to you.
All right, so here's going to be our recap for all the gates. So here we have our OR gate. Again, if at least one of these, A or B, is a 1, then it'll output a 1. You can see this here, down here, this table thing is called a truth table. But all this does is, okay, these are our inputs, this is our output. What are the different combinations that get us the outputs? So I can pause here for a second if you guys want to take some notes. I'd recommend taking notes on OR and XOR, and then just taking a specific note on the inversion bubble and what it does. Why is the NOT gate triangular shaped? It's mostly just because it has one input and it's just an easy way to distinguish between it. But
The,
again, you
yeah.
won't see a NOT gate.
The other reason is actually if you come to the extra session, you'll see we talk about op amps. And an op amp without any extra resistors and stuff is basically just a buffer. And a NOT gate, if you get rid of the inversion bubble, is also just a buffer. So actually, it's because it's like an op amp, and an op amp we use a symbol of a triangle to resemble. So
Okay. Do we have a Kahoot? Yes, we have a
we will
Kahoot in a
have.
minute. So I guess guys, give me like a reaction thumbs up when your guys are good with the notes on what OR and XOR and the inversion bubble do. Like a thumbs up reaction, I think you can do something like that. Okay.
Fortunately, we can't do book it because it's too late. We have not made it into these things.
Okay. I see a few. I'll wait for like another minute or two while you guys kind of like process this. This is just stuff that needs to be memorized. Like you can use the word to help you, but at the end of the day, kind of just make sure you're taking good notes. Okay. All right. I don't think we have too much time left, so I want to give as much
Yeah,
time to Kahoot. I'm just gonna get straight
yeah.
into it.
We're not gonna get to the SR latch. That's okay. It doesn't matter.
Yeah, that's fine. Okay, let's start the Kahoot, guys. Let me see if I can share the audio, but that might cause lag.
Are there any questions about logic gates or about transistors or what we've covered so far? I know I kind of fumbled the explanation for how MOSFETs make up a NAND gate, but it is important. As much as it seems kind of useless knowledge, it's very important to understand that because a lot of the behavior of how you have to build and the considerations you have to make when working with logic gates in the real world require you to understand that. What's up, Arav?
In the gates, what were like the numbers?
So the numbers
So
are ones and zeros. If you think of binary, a binary is ones and zeros, right? In the context of circuits, a one represents a high voltage, like 5 volts. A zero represents a low voltage, like 0 volts. Um, yeah.
Okay.
okay. Starts in 11. What the heck? Why can't I stop it from starting? Oh, okay. Guys, join up. When it hits like 40 something people, I'll end it. Ara, do you still have a question?
Oh no.
Okay, I'll lower your hand for you. Okay, when timer resets. Yeah, I'll
And
wait until
we
we have
won't
around 40 people, considering that we have 50 people in the lesson, then we'll begin.
we won't get to this in the slide, but when I send the slides out, if you care enough, you can look at it. Um, I was gonna talk about the most a very important logic circuit called the SR latch. I think it's starting. Okay, never mind. I'll stop yapping. Oh, it's a PNG.
I did not realize it was a PNG. That is funny. Winner, I guess top 5 will get bonus points for the week.
Oh,
Oof,
okay. So that was a
that's
NOR
bad.
gate, right?
Oh, can
Show
I
you
go
can
back?
press show media.
Can I go? It does show me that.
Actually, I'll
Oh,
link
this
to explain.
sucks. Oh my god. Okay, this drawing kind of sucks, but this is our oh wait, this is the I think this is wrong. Oh no, this is right. This is our OR
That's
gate,
right.
but is inverted. So this is our NOR gate. So our NOR gate is just an inverted OR. So you know when OR gives A or B is 1, it'll give a 1. We're inverting it, so it has to give a 0. So that's kind of the logic you guys are going to follow. Check what
So
the base gate is, and then see if it's inverted.
so for NOR, remember NOR is like neither nor, right? So if neither nor of the inputs is correct or is a one, then I get a one. Otherwise, I get a zero. Here, one of our inputs is a one, so I can't get a one. I have to get a zero. Okay, that's what a NOR gate does.
We can also use
NOR.
English. Okay. All right. I'm going to move on. Yeah, my bad for the bad image. I did not realize they would do that. All right. Keep going. Nice. Okay. I'll just briefly explain. So this is our AND gate. Oh, what the heck? And remember that since there's no inversion center, it's not going to be any of these because that's like when there's an inversion center, it's like not an AND. So this is our AND. There's no inversion, has to be AND. Okay. Next question. What? Why is this
Okay.
multi-select? Oh, what the? I thought I checked this. All right, this one might be sus, but like if it's weird, then I'll like fix it. Okay, I don't know why I gave both is right, but yeah, that one just won. So
That was
this
an
is our
OR
OR gate.
gate. Yeah.
I have no idea why that one was marked as correct, guys, but my bad. Yeah, that was just one. OR gate, both of them. Hopefully this
It's
one
okay.
isn't. Yeah, this one should take some time, but I gave you guys extra time here. I
I
would
guess
appreciate if y'all did not
try to
guess.
complete. Yeah.
I think this is like the most important part of this week's lessons for Scioli, so you guys should really be locked in. But I see a lot of y'all did actually get through the logic. Good job, guys. Good job. Okay. More time. Yeah, I don't know how I can edit it to give more time, but I can see.
You should try to do it quick. We don't want to give more time.
Yeah, I guess 30 seconds is enough for this.
Gotta
Yeah,
snappy.
especially this one. Yeah.
By the way, these are what when you put logic gates on breadboards, they look like this. These are ICs, integrated chips. Probably seen a video on YouTube of an integrated chip walking on a breadboard. So
Yeah.
the tune of Staying Alive by the Bee Gees.
Know exactly what you're talking about. Yeah, this is our second Kahoot.
Yeah, unlike some other ScioVirtual classes, we like to teach instead of
Yeah.
not teach.
If we have time, we can get into our teaching philosophy at the end because I think it differs. But for now, we'll just focus on the Kahoot. Nice, nice. I see a lot of y'all got that. Just the quick walk through here. We have our inversion center, and then it's our XOR gate, which you can tell by this like line back here. I know I didn't specifically talk about what it looked like on the slides. I didn't mention it, but yeah, and you see this line back here. That's our exclusive OR. Hopefully this one is like properly set up. When I say all gates, for this one, I mean all the logic gates that we discussed in class, which is all of the possible ones. So. Yep. This one's just pretty simple. Like A and B are just the two inputs. The order doesn't matter at all. I guess a lot of people got it wrong, but yeah, A and B doesn't matter which one's which. I think for a lot of these, I'm giving the answers to future ones as I discuss it, but I hope that's good. I hope you guys are learning. Nice. Yep, that's our OR gate. I'm not going to really explain that one. X is just exclusive. So it's that line in the back and means it's just an exclusive. This is a review from what Ishaan was talking about.
Where's the output, Jay?
Oh, the output is that bottom bit here. Just think that's the output. Okay, that was a bad circuit drawing. I should have drawn the output.
Well, yeah, that's ground.
That is ground. The output should have been like somewhere to the side or something. But okay, I'll explain this one. My bad. So in the actual circuit, the output's here. So make sure that, well, I guess not make sure. I need to make sure I draw that. But this is our PMOS. So we know that when A and B are both high, the transistor is off and it acts like a really large resistor. And since we know that they act like a really large resistor, most of this 5 volts isn't through. So yeah, my bad for not drawing the output, but I hope you guys got the intended meaning behind it because there will be further questions like this. Yeah, whoopsies, forgot to draw that. Okay. I'm going to kind of like rush through the rest of these so we finish on time. Yeah, there's still 20 questions left, so make sure you guys are, I mean, not make sure you guys are trying, it's like, if you aren't in top 5 right now, there's a good chance you will be later. Like, it's true. Don't give up now. Right. Wait, I think I might have put the wrong one here. Yeah, it should be 0. Let me show the medium. Yeah, that's our, oh, it's not 0. There's an inversion there. Yeah. So guys, remember, always look out for that inversion. See, I missed it on my cursory glance, but yeah, you have to make sure that you see that inversion there because this would have been 0 without it. Okay, moving on. That was probably one of the trickiest problems here. I guess out of which gate is the inversion bubble? Like that's a weird question. Which gate acts like an inversion bubble? It's a better way.
I love the butt gate.
Yes, the butt gate. Half of these had like Zand on them too. Okay. Let's see. Yeah. It's the NOT gate. The NOT gate will invert whatever input is given to it. And that's exactly what our inversion center does. Or not inversion center, sorry. Inversion bubble. Okay, this is a little better. I don't know why this like one is better, but whatever.
Butt gates are apparently a thing.
Really?
During the Cold War, they were used in some circuits. The Russians called them a Niet gate.
Yet. What the heck? Yeah, I'm not going to really explain that one. It would have been one. There's an invergence bubble, so it's 0. Okay, next. I'm going to try and go as quickly as possible. Oh, and by the way, that is not an inversion center or inversion bubble. I don't know why it's drawn like that, but this is just the output in case you guys.
Yeah, we have 4 minutes left.
Yeah, I know. I don't think we'll finish this exactly on time. I'm not really going
You
to
can
cover
just
that
stop it.
one. You guys can go over that later. Let's see. Yeah, if you need to go now, we can send the. Or I guess Ishaan can send the attendance code. But yeah, for the rest, I'm just gonna like go straight through it. Okay. Y'all should get this one pretty quick. Yeah. It's like ScioVirtual.org/attendance is always the link. Yep, that's our NAND. So that's our AND gate.
Yeah, again, it's the same thing with like solving actual circuits. Oh, okay. Solving actual circuits, right? So we didn't really talk about this actually. So this is good that that this is included. Um, to be clear, these are not MOSFETs. This is not the circuit symbol for a MOSFET transistor. These are the BJTs that were mentioned earlier, bipolar junction transistors. But yes, you did indeed get it right that they're transistors. But these are not the transistors that we talked about. These are different transistors.
Yeah, they are
So,
different transistors, but yeah, you guys should see the NPN. That's just, you should know from that. Y'all got this one, I believe. This is the hardest question out of, I think, the entire coot.
maybe we can stop it after this question and
Yeah,
just
I
take the
think this
leaderboard
will be
here.
our last one. Or I guess we'll keep going until like, yeah, no, I think this will be our last one. We don't have that much time. I don't want to push it over 3.
Yeah. This lesson kind of lacked compared to the previous ones. It's my bad.
It's fine. I think this lesson is going to be pretty important if you guys are doing like a circuit lab, the last half without the logic gates. So if you need to review anything from this and like the recordings and stuff, it'd probably just be the logic gates. Okay. Yep.
Yeah, that was a brutal one.
That is a really hard one. So in the way you solve this one is you would, yeah, I'm not going to do one more. The way you would solve this one is you give all the test outputs with zeros and ones. Like let's say A is 0, A is 1, B is 0, B is 1. And then you would see what that compares to. And in this case, it compares to the XOR logic gate. But again, this is like the hardest question on here. So if you got it, congrats. But yeah, I guess this would also be one of the hardest questions you would encounter on like a Siley test. Granted, you didn't have this in your notes. But, okay, I'm gonna end it here. I don't know how to end it early. And now, perfect. I'm locked. Okay, congratulations to these people. Let's see if I can get a full podium. What? Did I not get a full podium? Why didn't I?
It'll be in the recording. We can
They'll figure it out. If you were 4th and 5th, I don't think I started a new one, but I'm gonna close.
Attendance code is capacitor 8, right?
Yes.
Yep.
Okay.
I don't know how to close this. Don't join this. If I close this, will it close it? Did y'all get kicked out? Okay. Yeah. Y'all
So I got
I got second place and my nickname was Alpha Wolf, so my real name is Vikas.
Okay, that is good to know.
Uh,
If you
I
were
got
in the
first,
top
but
five
my
and you had a nickname, make sure to put it in chat
I
or
got
say it out
first.
loud.
My name is I put Nandan in the code, but my full name is Avatar Nandan. So
All right, we got that. Gus Alpha Wolf, nice. Who was fourth and fifth place? In case fifth place. Okay, Thomas. Got it. Attendance code capacitor 8. Yes, this is XKCD. Very cool. My goat. Yeah, see y'all. If you were fourth place, just like say something in chat. Otherwise, we'll figure it out from the recording. Yeah. Just a specific thing. I don't think I specified, but everything past this is like not real. Like the NOR X gate and like this is just odd. This is fictional. It's a bit. It's funny. Before the last question, but couldn't see after the last question.